Hi everyone, I welcome you again to my channel Econopatsala. A week before, I had uploaded a video on introductory econometrics. So I hope some of you have seen that. So in that video, I had discussed that econometrics deals with measurement of economic relations, and this is widely used for conducting research as well as for feeding to policy decisions both in public as well as in private corporate. So today is the first video where I'll be dealing with model specification in econometrics. This is the first step for econometric analysis. So if you remember, in the last session, I had told that econometrics is an interdisciplinary subject which combines economic theory with mathematical methods and statistical tools. So for model specification, we'll be heavily relying on economic theory. So economic theory basically provides the intuition to build an econometric model, okay, which I'm going to explain to you. So first of all, what is economic theory? Economic theory basically states an abstract relation between economic variables in a very simplified, structured and logical way. I'll explain about economic theory using two examples which are very popular in economics. First is law of demand. Law of demand tries to capture how different individuals, households respond in terms of buying various goods and services when price of those goods and services change. So the intuition suggests that when price of a particular good will rise, an individual will tend to buy less of that good, substituting for other goods and services. So this suggests there is an inverse relation between change of price and quantity of a particular good purchased or demanded, right? So now this relation I can express in terms of words as I have done in the screen here. So law of demand we can state as demand for a good is inversely related to change in its price. So this can be stated as law of demand. Similarly, in macroeconomics, another theory which is very popular, which is stated in terms of Keynesian consumption function. So this Keynesian consumption function tries to explain how the households will change their consumption expenditure when their income change. So we'll expect when income of a particular individual or that of a household will increase, so they will feel like richer and they will be spending more on consumption of various goods and services. On the contrary, when income of an individual will be reducing, we'll be expecting that there will be a similar impact in reduction of consumption spending of the household. So this theory, if I want to state in terms of what, I can say as income increases, consumption spending rises, but rise in consumption spending will be less than rise in income. Okay, so this we can express in terms of word, we can explain using words, but then for econometrics application, the theory need to be stated in a mathematical way. Okay, so because the measurement of economic relation require data, require mathematical methods to be applied. So the theory which we are stating in words, okay, will not be useful for econometric application unless we convert it into a mathematical form, right? So these two theories, if I want to express in a mathematical form, which we call a mathematical equation or a model, the law of demand I can state in the form of Q is equal to A plus B P, where Q is quantity of a particular good purchased or demanded, P is price of that good, so A is an intercept coefficient and B is a slope coefficient. So the role of A, B, I am going to explain. So this mathematical relation suggests when, if I assume B is negative, okay, then this mathematical relation suggests when price of a good will increase, the demand for good will decline. Please note, I'm assuming B to be negative. So it is in a way, capturing the inverse relation between P and Q. So this is expressing the law of demand in a mathematical equation or in a mathematical model. Similarly, the Keynesian consumption function, if I want to state it in a mathematical way, I can express as C is equal to A plus BY, where Y is income of a household, C is consumption of a household, or we can say Y is GDP of a country, that is aggregate income in a country, and C is total household consumption spending in that country. So this relation suggests that when Y will be increasing, C also will be increasing, okay, but rise in C will be less compared to rise in Y, because B we are assuming to be greater than 0 and less than 1. So if B is greater than 0, less than 1, that suggests that the relation between C and Y is positive, okay, but change in C will be less compared to change in Y in the same direction. That is, rise in Y will lead to rise in C, but rise in C will be lesser compared to rise in income. It particularly suggests that income can be saved or spent on consumption of goods and services. So when income is rising, part of that is used for raising consumption spending, and the remaining part is basically used for raising savings. So that's why entire increase in income is not used to raise consumption. Part of that is basically diverted for raising savings. So rise in consumption spending will be less compared to rise in income. So this is basically expressing economic theories in a mathematical way. Of course, the mathematical equations which we will be dealing with in the future will be very complicated. Okay, it will not confine to just one variable on the right hand side, because most of the phenomena like consumption spending or quantity demanded are influenced by a set of factors, not just one. But to start with, we are starting with a simple model, mathematical model, expressing law of demand and Keynesian consumption function in terms of just two variables. Now, if we'll generalize this type of economic theories, which are stated in the form of mathematical equation, can be stated in the form of mathematical equation, which you see before your screen, where I am expressing a general uh, a way of expressing an economic theory as y is equal to beta 0 plus beta 1 x1 plus beta 2 x2, so on and so forth, up to plus beta n uh, and xn. So what this mathematical model suggests, y, which is the dependent variable or endogenous variable. So dependent variable is the variable behavior of which we are trying to explain. So in the previous example, we are trying to explain how consumption spending of an individual change when income is changing. So what is explained is the dependent variable here, or we call endogenous variable, that is basically determined within the system. So endogenous, okay. So y is here endogenous variable, dependent variable, explained variable, or for simplicity we can say it is a left hand side variable, LHS. On the contrary, on the right hand side you have a set of variables. So I'm basically moving from a single variable on the right hand side to a set of variables on the right hand side. Those set of variables are x1, x2, x3, etc. up to xn. So these are different variables like income, wealth, maybe interest, general prices. So these are set of the variables which are basically impacting the dependent variable y in this case, right? And beta 0 is the intercept coefficient, like we had a in the previous model, and beta 1, beta 2 up to beta n are known as partial slope coefficient. So the meaning of partial, this may be new for some of you. By partial, this suggests, say for example, beta 1 is a partial slope coefficient which captures the impact of change in x1 alone on y, keeping other variables constant. Other variables are here x2, x3 up to xn. So that way it is capturing partial impact of x1 on y. So beta 1 is a partial slope coefficient. Similarly, beta 2, beta 3 up to beta n are partial slope coefficients which are trying to capture the impact of change in that particular variable with which it is associated on the dependent variable. Okay, so if x1 is income, then beta 1 captures the impact of change in income on consumption spending y. If x2 is wealth, beta 2 captures the impact of change in wealth on dependent variable consumption spending. Okay, so when we are trying to account for change in a particular variable like income or wealth or general prices, so only we are allowing change in that particular variable, keeping other variables constant. So beta 1 measures the impact of change in income on the dependent variable y, keeping all other variables x2, x3 up to xn constant. Okay, please note this. Now, yeah, so I have already explained beta 0 here is the intercept variable, and intercept, not variable, intercept, and beta 1 up to beta 1 up to beta n are partial slope coefficients. So for some time, it may be today's session and maybe a couple of sessions, I'll confine myself to a simple mathematical model which is basically expressing an economic theory, and this simple mathematical model will have one variable on the left hand side, and that is dependent variable, and one variable on the right hand side, because using a simple model like this, which is a two variable model, is easier to explain the methodology of econometrics to many of you who are not very sound in mathematics. Over the time, we'll be moving from this two variable model to a n variable model, which can account for large number of variables on the right hand side. So in a two variable model, okay, we'll say beta 1 as slope coefficient, not partial slope coefficient. So the difference is here just one variable. Okay, so we are calling it slope coefficient. In a n variable model, we call these all the coefficients associated with the right hand side variables as a partial slope coefficient. Now, one more thing about the econometric model. We'll be popularly discussing about ordinary least square and different least square methods for estimating an econometric model. So in those models, we'll additionally assume that our mathematical model is linear. So what do I mean by linear? By linear, we mean the exponent of the intercept and the slope coefficient is 1. That is beta 1 raised to the power 1, beta 0 raised to the power 1. We don't mind if the exponent of the right hand side variables are different from 1. That is, the power of x1 can be 2, can be 1, can be 3. So there is no restriction on that. But we'll assume that the coefficients like the intercept and slope coefficient, they are raised to the power 1. And these varieties of models are popularly referred as linear model. Okay, that is linear in coefficient. About that, I'll be revisiting again when I'll be discussing about assumptions of classical linear regression model in my next session. Now, just to start with a little bit about interpretation of a mathematical model. So assume I have specified a Keynesian consumption function two variable model where C was A plus BY, and after a estimate, the estimation procedure I'll be discussing as we move on. Today I'm only discussing about specification, but then you'll be wondering what this A and B stands for. So assume I have estimated this and I got the value of A as 24,000 and the value of B as 0.7. So what is the significance of these estimated coefficients? So here my 24,000, which is basically estimate of the intercept coefficient, suggests that if the value of the right hand side variable, that is x1 or y here, is equal to 0, then the value of C on an average will be 24,000, right? But in economic interpretation, this A has a meaningful interpretation only if you have large number of numerical value of x1 as 0. Assume if I am using y as GDP. So GDP values are certain million or billion. So obviously GDP value will not be 0, large number of values. So in that case, this A, estimate of A, is not meaningful. Okay, it's just a sort of a number. Now there in econometrics model, there is heavy reliance on interpretation of the slope coefficient. So here the estimated value of B is 0.7. So what it suggests? It suggests that if say y, which is our right hand side variable, increases by 1 unit, then the left hand side variable, that is a dependent variable consumption spending, will be increasing by 0.4 on an average. So if y is increasing by 1 rupee, C will be increasing by 0.7 rupees on an average. If y is increasing by 1000 rupees, then C on an average will be increasing by 700 rupees. So this on an average, what I'm telling, what is this interpretation? You'll be having more clarity on this when I will basically estimate a model. Okay, I'll be discussing about the estimation of the model and interpreting that. You'll have more clarity on that. Right. So now just to give a feeling that how a B or A will look like after we estimate the mathematical model. Now, we started with economic theory getting expressed in word, then we come to a mathematical model, right? Now this mathematical model, you can easily connect the specification of a model, okay, to the relationship between the dependent variable and the independent variable, that is the right hand side variable and the left hand side variable. So one thing is choosing the variables on the left hand side and right hand side. For that we get guidance from economic theory, like we specified B is negative in a say basically we included income on the right hand side, consumption on the left hand side, guided by Keynesian consumption function. Then we introduced price on the right hand side and quantity demanded on the left hand side, guided by the law of demand. And the coefficient, sign of the coefficient in the consumption function, in the Keynesian consumption function, we assume the value of B to be greater than 0, less than 1, guided by Keynesian theory. Okay. Similarly, law of demand suggests the sign of B in the law of demand equation will be negative. So that way, our economic theory guides what variables to be included on the right hand side and the left hand side of the mathematical model, and the sign of the coefficients. Now one more thing is there has to be also specification of the mathematical form of the equation. So if we expect the relationship between variable y, which is the dependent variable given in the y-axis, and x, which is the independent variable given in the x-axis, has a linear form as given in the linear equation on the graph, then the mathematical form should be again a linear form, which is, as many of you may be familiar, the linear equation form is y is equal to beta 0 plus beta 1 x, right? On the other hand, if the theory suggests that the relation between the left hand side variable and right hand side variable can be given in the form of a rectangular hyperbola, as you can see in the graph before you, particularly when we talk about money demand, okay, particularly classical QTM, quantity theory of money, which is expressed in Cambridge version, that states M is equal to KPY. So there Py I can write as M over K. So M is an exogenous variable determined by the central bank, this is money supply, and K is assumed to be constant, that is the propensity to hold money, to demand money. So if these two numbers are constant, then M over A is constant, then product of P and Y will be a constant, right? So in this relation, when P will be rising, Y will be falling. When P will be falling, Y will be rising, so that the product remains constant. Okay, and this relationship is given in this graph in front of you. So not necessarily the econometric model which will be specifying has to be in a linear form. It can include n number of possibilities. It can be a quadratic form, it can be a cubic form, it can be a parabola, rectangular parabola, it can include anything. But in most of the models where we are using least square procedure to estimate, we basically impose a restriction that the exponent of the coefficients is 1. Okay, there is no restriction on the exponent of the variables on the right hand side, right? So then I cover two things about, in fact, three things about model specification. It deals with selection of variables, the left hand side variable and right hand side variables. It deals with the sign of different variables and restriction on numerical value of different coefficients, not variables, coefficients. And then what mathematical form our mathematical model, which is expressing the economic theory, will take, that will again be determined by economic theory. So economic theory guides us in specification of our econometric model. Now, the mathematical model has many deficiencies when we talk about the behavior of different economic agents. Let me talk about the Keynesian consumption function. So the way we expressed earlier in a mathematical form, this suggests if income is increasing by 1000 rupees for a household, their consumption spending on an average will increase by 700. On an average it may be, but then every household, every individual has a unique way to respond to change in income. Similarly, if I'm talking about law of demand, a given price change doesn't impact the behavior of each individual, each household exactly in the same way. Some households may be price sensitive, so when price is rising by 1 rupee, their consumption spending may fall by a larger amount if they are highly sensitive to price changes. Some individuals could be price insensitive. For them, it doesn't matter if price is changing. They want to maintain their consumption basket at the same level or at very close to the initial level. So in that case, a given change in price, say by 1 rupee, will reduce their consumption spending by lesser amount. So the individuals do not behave like a machine as specified in a mathematical model. Now this randomness, the stochastic nature, what we call a unique way of different individuals responding differently to the same situation, okay, need to be incorporated in economic analysis. So we have to move beyond a mathematical model which assumes as if every individual is behaving in the same way when there is a price change. Like in the earlier model, when the slope coefficient of y in the Keynesian consumption function was estimated to be 0.7, say, it suggests that whenever income is increasing by 1000 rupees, for every household, consumption expenditure will rise by 700. Obviously, it is not. Okay, different households will raise their consumption spending by different amount. Some may raise their consumption spending by 700, some may by 600, some may by 900, right? So this randomness of response of the household to change in their income, okay, is not properly captured in a mathematical model, right? So there is a need to improve the mathematical model and build an econometric model. Okay, so the econometric model is given in front of you in the general form. So here you see the mathematical model in general form, which I discussed earlier, and this econometric model only difference is the last term on the right hand side, which is u. So the u is added to a mathematical model to get an econometric model, right? So what is this u? U, we call it stochastic error term or random error term in an econometric model. So this u has tremendous significance in econometric analysis. This u captures several things. The u captures partly the randomness of the dependent variable. Randomness of the dependent variable meaning, as I said, how the dependent variable changes for the same change on one of the right hand side variable, okay, depending on the degree of response of different individuals. So which we consider as random or stochastic. It is not fixed, right? So this partly u captures the randomness of the response of the individuals to a particular economic situation, change in economic situation, right? It also captures the randomness of the missing independent variable. Say, assume, there are 5 variables which are impacting the dependent variable on the left hand side, and the econometric modeler has included only 3 or 4, has missed 1 or 2. So the random impact of those missing variables on the dependent variable is also captured by the stochastic error term u. And thirdly, the stochastic error term also captures the measurement errors. See, ultimately, if you want to estimate an econometric model, we have to collect data on the dependent variable, on the right hand side variables, independent variables, right? And when we are collecting data, there could be some measurement error. Details of measurement error we'll be discussing one session. So just briefly I'm mentioning, maybe conceptually there is a problem the way the dependent variable is measured, okay, or while collecting data and tabulating data, there is a human error in inserting that figure or keying that figure, right? So there could be various reasons uh, which are basically we put that in terms of measurement error of the dependent variable. So that error also is captured by our stochastic error term u. Okay, so why as I'm telling that the stochastic error term is tremendously important for econometric analysis. In next session, I'll be discussing about classical linear regression model assumptions. In that session, I'll be discussing that there is something called Gauss-Markov theorem, which guides or which suggests that if certain assumptions are satisfied, the sample estimate of a particular slope coefficient will be giving us idea about population parameter. What do I mean by this population parameter and sample estimate? Assume we want to estimate the law of demand, okay, and law of demand should be applicable for any individual, any household in general. So there could be billions of households, okay, in the world, okay, or maybe some millions of households in a particular country. Now, for an econometrician, it is impossible to ask each household how you will respond to change in price of a particular good you are consuming. So in practice, what the econometrician does or the statistician does, they collect data from some finite number of households, which is the sample of the population. Okay, so population when will including every household in our analysis, but that is practically impossible. So we'll be confining to some hundreds, thousands, okay, of the households, and for them we'll be collecting information on how they respond to a particular change in a particular situation, economic situation, and based on that data we'll be estimating the intercept coefficient or slope coefficient. The number 0.7, as I told you earlier, that is based on a sample. Okay, so that is a sample estimate. But as a researcher, your conclusion about an economic relation is not restricted to a sample. It has to be universal. So you are trying to get conclusion, inference on whether in general, if there will be change in price, the consumption spending of a household will fall or not, right? So that is the corresponding coefficient we'll call a population parameter. So B for the sample is sample estimate, B for the population is population parameter. So using econometrics we will be estimating B from this sample. We'll be getting this sample estimate like 0.7. But based on that, we'll make a conclusion about population parameter. So these details I'll be discussing later on. So the end objective of econometric analysis is specify econometric model, collect data and estimate, and make inference about your theory, population parameter, right? So for that, Gauss-Markov theorem is critical, which suggests if certain assumptions are satisfied, then we can make inference about population parameter, about the empirical relation between two variables or more than two variables, okay, deriving from our sample estimate. So that's how these assumptions are very important, and we'll be discussing about some 7 to 10 assumptions, and among them most of the assumptions are about the properties of U, stochastic error term. Okay, so if those properties are satisfied, then we can use a methodology called ordinary least square, which is very simple, and the sample estimates derived by applying OLS can tell us, can sort of lead us to infer about the population parameters. So that's how the stochastic error term is very important. So just quick recap, we started with economic theory, and I told that the model specification in econometrics, based on economic theory. Okay, economic theory suggests us what are the variables to be included on the right hand side, left hand side, what will be the sign and numerical value restriction about on the coefficients, and what is the mathematical form our econometric model should take. So the theory can be expressed in words, but it is not useful for us unless for econometric application unless it is converted into a mathematical form. So we moved from theory expressed in words to theory in terms of a mathematical equation, but then the mathematical model is not adequate to capture the randomness of different agents in economics. So we had to build a econometric model, okay, adding the stochastic error term to our mathematical model. Okay, and this stochastic error term is of overwhelming importance in econometric analysis. The first thing I said, if certain properties are satisfied about U and of course some additional things, then the OLS application and getting sample estimates using OLS application can help us to make conclusion about population parameter, the economic relation in general. Okay, so that's how the stochastic error term in econometric model is very important. Okay, so when I'll be talking about assumptions, there I'll be discussing about the necessity that the econometric model has to be correctly specified for making our econometric analysis meaningful. So the correctness in terms of specification of the model requires selecting right variables, not to miss a variable on the right hand side, and not to include an unnecessary variables on the right hand side. Then availability of data, okay, on those variables, and ensuring that those variables are measurable, and functional form. By functional form I mean whether it is a linear equation or a quadratic equation or an inverse function, mathematical functional form. So these three things are critical, okay, and any error in this regard will make our econometric model erroneous, okay, problematic. So the first step in econometric analysis is constructing a correct econometric model. Okay, and of course we'll be discussing later on that there are different tests which econometricians use: the Ramsey's reset test, Haussmann test, information analysis based on archaic information criteria AIC, Bayesian information criteria BIC, residual analysis. This residual analysis about different properties of the stochastic error term U. So those things we are going to discuss. Okay, so this was the first session in my econometric basic econometrics, so where I discussed about specification of the model. In the next session I'll be perhaps discussing about the estimation of the model specified using OLS. That is the first thing I'll start with. Okay, and then I'll move to the assumptions, classical linear regression model assumptions, which are critical for econometric analysis, and then I'll talk about the inferences, how we'll discuss about hypothesis testing, how we'll make a conclusion about economic theory based on our estimation of the econometric model using OLS or some other procedure of estimating an econometric model. So thank you for listening to me. I'll be happy if this session was useful for you, and you may please write to me either in this channel or in my email ID about any additional thing you want to hear from me, or if some point is not clear to you, you may please write back to me and I'll be happy to elaborate on that. So thank you for listening to me.